Hello, let's start with Chapter 3. This is Section 3.1, graphing using the first derivative. So if the graph of the original function f of x is increasing, then the slope is positive and the derivative is positive. Okay? So basically we're saying look at a function and the graph is increasing. So it can look like this, it can look like this, it can look like this. The slope of all of these is going to be positive, and we know the derivative is the slope of the tangent line. So if the slope is positive, that means the first derivative is also positive. Similarly, if the graph is decreasing, then the slope is negative, and the first derivative is also negative. We can have maximum and minimum points, okay, of a function. So this graph is increasing. This is called a relative max. It's the max in that area. Some books will also call it the local max. And you can have a relative min or a local min. Okay, and look, notice this graph here. There's a relative max and min even though the derivative is undefined. Remember we talked about corner points. The derivative is undefined at corner points, but that still is the maximum in that area. Okay, similarly this is the minimum. So what does that mean mathematically, a relative max or min? If the f has a relative max at c, if f of c, which means the y value at c, is greater than all other y values in that area, okay, near c. And a relative min means the y value at c, right, where c is your x value. So c is your x value, you look at the y value, so for example here, let's call this c, this is f of c, that is the lowest y value in that area, right, near c, so we call that a local min. A critical number is a value, is an x value where the derivative is 0 or undefined, okay? And you have to be cognizant, it's an x value in the domain of f, okay? So you're only looking at values for which the function is defined. That's the domain. Let's do an example. So we want to graph this function by hand. So first thing we have to do is find the critical numbers. Well, critical numbers are where the derivative is 0 undefined, so let's find the derivative first. So f prime of x is 3x squared minus 24x minus 60, okay, and it says find the derivative, set it equal to 0, so we set that equal to 0, and I want to solve for x, okay. Now right away I can see, let me factor out a 3, x squared minus 8x minus 20 equals 0, divide both sides by 3, okay. This is just doing, the calculus part happened here, right? We found the derivative. The rest of this is just the algebra. Now we want to take, factor this, so I want to think factors of negative 20 added to give me negative 8. Well, 10 and 2 give me 20, and I want negative 8, so the 10 has to be negative. So x minus 10, x plus 2 equals 0. Set each of these equal to 0. So x equals positive 10 and negative 2. Okay? So we found the derivative, set it equal to 0, and solve for x. The other way to find a critical number is to, you also have to check that you take the derivative, and wherever the derivative is undefined, that will also be a critical number. Okay? Here, it's a polynomial, so it's defined everywhere. The derivative is a polynomial, quadratic, it's defined everywhere. Okay? So we call these our critical numbers. Okay? That's the first step. Second step is to make a sign diagram. So you make a number line, and here is my first critical number, here's my second critical number, 10 and negative 2. And we want to find out where the original function is increasing, decreasing, right? So we can look at, remember, if it's increasing, the derivative is positive. If it's decreasing, the derivative is negative. So we want to make a sign diagram for the first derivative. So what you're going to do is pick a test point. So I want to pick a test point below negative 2, and let's say I pick negative 3. Okay? So we're going to do f prime of -3, and you're going to take -3 and plug it into the derivative. And you can use this table if you want to help you. So my test point was -3, and then a number between -2 and 10. Let's pick 0. Okay, make it easy for ourselves. And then a test point above 10. So let's say 11. Okay. And where are we plugging this into? We're plugging this into the first derivative. Okay, what was the first derivative? 3x squared minus 24x minus 60. Okay, so let's do that. Let's use the calculator to do this. Now let's use the table function. So what you're going to do is do y equals and plug the first derivative into here. 3x squared minus 24x. And we want to test the points -3, 0, and 11. So what I'm going to do is use the table function. So you go to second window, which is table set, and I want it to be ask, and then second table, and we have the points -3, 0, and 11. Okay, so the values are going to be 39, -60, and 39. Okay, again, we did this from looking at the table. And this tells us that the whether the graph is increasing or decreasing. Okay, so 39 at -3, the first derivative is positive. This first derivative at 0 is negative, and this is positive. Uh-oh. Okay, I don't know what happened there. Okay, well that's positive, so let me not. Maybe it doesn't like me writing on the table. Alright, so positive, which means the graph is increasing. At 0, the graph is negative, so it's decreasing. And here the graph is also increasing. Okay. So now I can sketch the graph using this information. And what I can also do is at the second or at the critical points, we know the derivative is 0, right? Remember we did this? We did the derivative equal to 0. So at the derivative equal to 0, the graph is horizontal. Okay, that's where we have that relative max or relative min. Okay, like this and like this. And then it says it helps to find, now we can sketch the graph. Let's find the values of the critical points in the original function. So we want to take the original function, which was x cubed minus 12x squared minus 60x plus 36. Okay. And what you're going to do is plug that. Now let's do that in excuse me. Plug that into y equals. Now this was a derivative, right? So we don't need that. We need the original function. X math 3 x cubed minus 12x squared minus 60x plus 36. Okay. And we want to plug in the critical numbers into this function. So I'm going to go to second table, and at 10 and at -2. Okay, so let's put that here. Okay, so f of 10. Now we plug this into the original function to find the actual y values. Okay, so let's see. At 10 it was negative 64. And at negative 2 it was 100. Okay. So let me just count by hundreds here. So this is 100. This is minus 100. So at negative 2, the graph is 100. At 10, 1, 2, 3. Oh, it's not going to go all the way. So let's make this go by negative 2. Let's make that here. And this is 2, 4, 6, 8, 10 is here. Okay. And at negative 2, the graph is 100. So that's this point right here. And at 10, it's negative 764. So 1, 2, 3, 4, 5, 6, 700, 800. So that's negative 700, and that is roughly somewhere here. Okay. We're doing a sketch. And now we can look at our sign diagram and see before negative 2 the graph is increasing. So increasing looks like this. At negative 2 it's flat. After, between negative 2 and 10 the graph is decreasing. And then after 10 the graph is increasing again. Okay. So that is roughly what the graph looks like. Okay. If a function f has a critical number c, then at c the function has a relative max if the derivative is positive before c and negative after c. So this, if you draw it out, it's very easy to see this. Okay. So if the graph is positive, or the derivative is positive, that means the graph is increasing. And then if the derivative is negative, that means the graph is decreasing. Do you have a max there? Yeah. Okay. And if the graph is decreasing and then increasing, do you have a min there? Yeah. Okay, so that's all that is saying. Use the steps above to graph this function here. Okay, so let's do this from scratch. So first thing you want to do is find the critical numbers. Okay. So to find the critical numbers, we need to take the derivative and find out where it's 0 or undefined. So we get negative 4x cubed plus 12x squared. Right? And the derivative of 20 is 0. Now I need to set this equal to 0 and solve. And is this undefined anywhere? This is not undefined anywhere. So it's defined everywhere. It's defined on its domain. It's a polynomial, right? So we don't have to worry about the undefined part to find critical numbers. We just have to worry about the setting it equal to 0 part. And so let me pull out a negative 4x squared. And then I'm left with x minus 3. Set that equal to 0. Okay. And when I set both of these equal to 0, I get negative 4x. Now be careful, I'm going to write this middle step in here because people forget to do this part, right? That means x equals 0. So I have two roots, or two values where x equals 0, x squared, and I have one value where x equals 3. Okay? So what are my critical numbers? X equals 0, comma 3. Okay? That was the first step. Second step is the sign diagram. Sign diagram for f prime of x. Okay. So I make a line. We're going to take the first derivative and let's put these, so this is a number line, so we have x equals 0 and x equals 3. Okay. And we want to take the critical numbers and plug them into the first derivative. So I want to, or not the critical numbers, I'm sorry, test points. So we want to find test points. So what are our test points? Let's pick a number below 0, negative 1. Let's pick a number between 0 and 3. Let's pick 1. And a number above 3. Let's pick 4. Okay? And then we want to take these values, these test points, and plug them into the first derivative. Okay? I'm writing extra stuff for you. You don't have to put this in. I'm just clear that these are the test points. Alright, so let's do that. Y equals negative 4x cubed plus, oops, that's not cubed. You can hit the up caret also. Let me do that, because some of you have the TI-83 plus, so that would look like this. Okay. Just 1 second. Let me turn off my, let me change the settings so that it looks like the calculator that some of you have. So let's do y equals negative 4x cubed plus 12x squared. Okay, that's what you'll see. And then we want to do the table function, and I want to plug in my test points, negative 1, 1, and 4. Negative 1, 1, and 4. So now we'll see it's 16, 8, negative 64. So this is 16, 8, and negative 64. The actual numbers don't matter, it's whether it's positive or negative, right? So that tells me that this is positive. The graph, if the first derivative is positive, the original function f is decreasing. Second derivative is positive, again, first derivative again is positive, so my original function is increasing. Did I say decreasing? I meant to say increasing. So this is positive, increasing, and here negative 64 is negative, so that means my original function is decreasing. Okay. And then the third step you want to do is to sketch it and define those values. Okay, so let's take our critical numbers and plug them into the original function. Okay, so you got to go back to your calculator, and we get negative. We got to put the original function in, so that's negative x to the 4th plus 4x cubed. Okay, and you have plus 4x cubed minus 20. Okay, and then we want to plug in our, so you go to second table, and let's plug in our critical numbers, 0, 3. So we get negative 20 and 7. So f of 0 is negative 20, f of 7, f of 3 is 7. Right? F of 0 is negative 20, f of 3 is 7. So now you take 0, and so let's see, let's count by 4s. So we get negative 4, 4, 8, 12, 16, 20, and that's 0, negative 20. And if it helps you, you can write out the points. My points are 0, negative 20, and my point is 3, 7. These are actual points on the graph of f. Okay, 3, and then this is 4 and 8. So this is 3. And 7 over here. Okay. And we want, before 0 the graph is increasing, between 0 and 3 it's increasing, and after 3 it's decreasing, and then let's rewrite that at 0 it's flat, and at 3 it's flat. So that's the shape of our graph. Okay. So it increases, goes flat, increases, goes flat, and then decreases. So that's what the graph of that looks like. Now, you're saying, what is the point of all this? We can use our calculator to graph this. Yes, we can, but I'm on the exam and on the quiz, I'm going to ask you to show all these intermediate steps, right? And your work has to match. You can always use your calculator to check. Okay, so we have the original function in there, minus 4x minus negative 4x to the fourth plus 4x cubed minus 20. You can do zoom 6. Okay. And my x-axis goes by 1 and the y-axis goes by 4. So let me change that window. And remember, this point is negative 20 right here, so we have to see that on our graph. So let's change the window to go from, let's say, negative 5, right? This is negative 5 to 10, that's fine. The y-man, let's change it to negative 30, and the y-max is 10, that's fine, but my scale is going by 4s. Okay, and that's what we have here. So before, right, calculators and computers, this is how we would sketch graphs by hand. And this shows you a lot, right? This is part of learning calculus, how it's like the behind the scenes working of these functions, right? All right, let's look at rational functions. What is a rational function? A rational function, when you think of rational, think of ratio. Ratio of polynomials. We've done this before, okay, in the previous video for this class. And what are asymptotes? Asymptotes are lines where the graph approaches but doesn't reach. Okay, lines where the graph approaches but doesn't reach. So look at this one. Rational function is p of x and q of x. Now p of x and q of x are the polynomials. Okay. A rational function has a vertical asymptote. Oh, and the one thing for rational function is where the denominator cannot equal 0. Right? So q of x cannot, oh lordy. Where the denominator cannot equal 0. So q of x cannot equal 0 here. Okay. So a rational function has a vertical asymptote if the denominator equals 0, but the numerator does not equal 0. So c is the point where the denominator equals 0, right? That makes the whole function undefined, and that's why we have a vertical asymptote there, because the graph will approach that function, but never actually reach it. Okay. So the graph will approach that function, but never actually reach it. It can't because it's undefined there. The denominator is equal to 0. Okay. A horizontal asymptote, y equals c. Now remember, horizontal is the line y equals c if the limit as x approaches infinity or negative infinity of that function equals c. Okay, so if I wanted to graph a rational function by hand, first thing you have to do is find the asymptotes. Then you can use that same three-step method we've used above here to graph the rest of the function. Okay. So let's do this one from scratch. So first thing you want to do is find the vertical asymptotes. To find the vertical asymptotes, set denominator equal to 0 and solve. Okay. So we have x minus 1 equals 0. So therefore x equals 1. That is my vertical asymptote. Okay. The horizontal asymptote, you want to divide out the highest term in the denominator. So divide out the denominator's highest term. Okay, you can add that in there from the numerator and denominator, and find the limit as x goes to positive and negative infinity. So let's do this. The limit as x goes to, let's look at positive infinity. of 2x plus 3 over x minus 1. Okay? What's the highest term in the denominator? X, right? We don't have x squared, we don't have x cubed, we have x. So we're gonna, dividing is the same thing as multiplying by the reciprocal. Okay? So then we have the limit as x goes to infinity. Now let me put this intermediate step in there, okay? Since this is the first time we're doing this, you don't have to do this every time. I mean, you don't have to put these steps in every time. So we get 2x times 1 over x, and then 3 times 1 over x. Remember, you have to distribute this to all terms. And then x times 1 over x minus 1 times 1 over x. And what do we get here? Alright, 2x times 1 over x is 2, plus 3 over x divided by x times 1 over x is 1, minus 1 over x. Okay? And then as x goes to infinity, remember 3 over infinity is a, goes to 0. Right now we're plugging infinity in for x's, so this goes to 0, this goes to 0, and now we just have the limit, whoops, the limit as x goes to infinity. Oh, we already did that, so we don't need this, right? So this is just 2 over 1, which is 2, so that's your y value. So that's your horizontal asymptote. Okay? So we have our vertical asymptotes, we have our horizontal asymptotes. Now we can do the critical numbers. Before I move on, some of you have taken pre-calc or maybe calc somewhere and you've remembered this thing that if the degree of the numerator is greater than the degree of the denominator, then you do this. If the degree of the numerator is equal to the degree of the denominator, you do that. And if the degree of the numerator is less than the degree of the denominator, you do that. So there's some, if you have that memorized, that's fine. If you don't worry about it. I don't memorize that. I use this technique here because it always works, right? And it saves some brain space so I can memorize other important things. So do some practice with this, and you'll see that this works. And this also works for negative infinity, right? Some problems you have to do negative and positive infinity separately. This one also works for negative infinity because when you plug 3 into negative infinity, you get 0. 1 over negative infinity goes to 0. We still get 2 over 1. Okay? Now let's find the critical numbers. How do we find the critical numbers? Take the derivative. So remember, for this we have to use the quotient rule. I'm going to call this f, call this g. Quotient rule tells me f prime g minus g prime f over g squared. And so we're going to do that here. Okay? Let's write out our f prime, which is 2, g prime, which is 1. Right? If this helps you, by all means, please do this to keep yourself organized. Okay? And g equals x minus 1. Okay? Now f prime is 2, g is 1, f prime, oops, sorry, g is not 1, g prime is 1. F prime g. X minus 1. F prime g minus g prime, which is 1, times f. 2x plus 3 divided by g squared. X minus 1, quantity squared. Okay. Let's simplify this out. We get 2x minus 2 minus 2x minus 3 all over. You can leave the denominator alone. You don't have to FOIL that out. Okay. Now we get 2x minus 2x are gone. We get negative 2 minus 3, which is negative 5 divided by x minus 1 squared. Now remember, to find the critical numbers, you got to set this equal to 0, and you got to find out where this is undefined. Let's look at the 0 case first. Now if you have a fraction, the only way you're going to get a fraction equal to 0 is if the numerator, if the top is equal to 0. The top for this will always be -5. So can this equal to 0? No. This can never equal 0. So we don't have any critical numbers where this equals 0. Okay? I'm going to say here set equal to 0. Now, you can also find the critical numbers where the derivative is undefined. Remember that? This is one of the very beginning things we did, where the derivative is undefined. So let's look at the derivative. Where is the derivative undefined? Remember, this is a rational function, so where the denominator equals 0. So f prime of x is undefined when the denominator x minus 1 squared equals 0. If I square root both sides, then I get x minus 1 equals 0. Right? And then you get x equals 1. Well, we already saw x equals 1. X equals 1 is a vertical asymptote, right? So this is a critical number, but it's also a vertical asymptote. Okay, and that is our only critical number, x equals 1. Let's make the sign diagram now. Okay, x equals 0. Now instead of putting the horizontal arrow that I usually do above, that I did above, we're going to put vertical asymptote because we want to indicate that the graph does not exist there. And then let's find the test points. Let's plug in -1. Now remember, you're making a sign diagram for the first derivative, so you're plugging these into the first derivative, not into the original function. Okay, -1 and f prime of 2. Alright, this might be easier for me by hand rather than doing this on the calculator, so let's find f prime of -1. So here is, remember I took the derivative and got it down to this point here, okay? So that is a simplified version, so we get -5 over -1 minus 1 quantity squared. So that is -5 over -1 minus 1 is -2, squared is 4, so that's -5/4. Okay, when you plug 2 into the function, -5 over 2 minus 1 squared, you get -5 over 1 squared, which is -5. Both of these are negative, so that means this function is always decreasing. Okay. Third step, before we sketch the third step, let's go ahead and put 0 into the function. Remember, we want to, oh, we can't plug 0 into the function. Oh, I'm sorry, did I make an error here? Oh, I apologize. See, this happens. This is a good way to check yourself, because remember, we always want to find the value at the critical number, and then we plug it in, and I saw, wait a minute, I know when I plug it in I should get a vertical asymptote, so this should say x equals 1. My apologies. And is -1 still below 1? Yeah. And 2 above 1? Yeah, that works. Alright, so let's sketch this graph. That's a good thing with math, is you can always check yourself. So let's see, at 1, so let's call this, at 1 I have a, what's my line doing? This is the line x equals 1, right? That's my vertical asymptote. Before 1, the, and where's my horizontal asymptote? Let me look at that. Horizontal asymptote is y equals 2. So here's 1, 2. Okay. So now I know before 1, the graph is decreasing. Okay, so that means it's got to be either in this area or this area. Well, if it's in this top area, it can only go up, right? But that's not increasing. So I want to do decreasing. So it has to look like this. Right? It never approaches the horizontal, never approaches the vertical. It gets close. And then after 1, it's also decreasing, which means it's going to be in this area going down. Okay? If it was in this quadrant, it would be going up, but it doesn't do that. It goes decreasing. Okay? So that is what your graph looks like. Okay? So for vertical asymptotes, or for rational functions rather, find the vertical and horizontal asymptote first, right? That was our first step. Second step, then you find the critical numbers, then do the sign diagram. And then if you need to find f of the function, or f of the critical numbers, if there are any, then you sketch the graph. Okay? So we'll continue with section 3.2, where we bring in the second derivative, and then we'll do sign diagrams for the second derivative. If you have any questions, please get in touch with me. In the meantime, please work on your homework.